this video, let's discuss about another important matrix in graph theory, that is cut set matrix. It is usually represented by Q matrix. This matrix is used for nodal analysis. Therefore, it is also known as node voltage matrix. Or in other words, it is a matrix used to find branch voltage in terms of tree branch voltages, that is twig voltages. It is obtained by using current balance equation. Here also we are applying KCL, but KCL is not applied at nodes. This idea is totally different from conventional method of applying Kirchhoff current law. Let's consider three branches of a network, say 1, 2 and 3. Say this is branch 1, this is branch 2 and this is branch 3 of a given network. So that branch alone is drawn here. Say the current direction in each branches, branch 1 current direction is this one, branch 2 current direction is this one, and branch 3 current direction is this one. Consider an imaginary line 1, 1 dash which is cutting these branches into two parts. Then we can sum the current crossing this line, these imaginary lines. That sum is 0. So KCL we can apply it across this imaginary line. Under this case, we are assuming that left to right current as positive. So this is left and this is right towards this line, imaginary lines. So the current direction is moving from left to right. So I1 is taken as positive and I2 is taken as positive. As this current is I3 current is moving from right to left, this current is taken as negative. Now we can write down this equation like this. So I1 is positive, I2 is positive and I3 is negative. So their algebraic sum at this imaginary line 1, 1 dash is 0. So that means here we are applying KCL at this line, imaginary line. That line is known as cut set. Cut set is nothing but it is dividing the branches or network into two parts. So here this line 1, 1 dash is dividing these branches into two parts. So when we are applying KCL at these imaginary lines or cut set, left to right current is taken as positive and right to left current is taken as negative. So this is the KCL equation at cut set 1, 1 dash. The same thing we can see from network also. Here we can cut the network into two parts by drawing a line 1, 1 dash. In this line 1, 1 dash, several branches get intersect. Now if we are summing these branch currents, their value will be 0. That is KCL at this cut set 1, 1 dash is 0. The branches intersect with this line 1, 1 dash are this current is there and this branch current is there and branch current through these elements and these branch currents. So when we are considering these intersecting branches, current at this cut set is 0 according to KCL. So when we are applying KCL at cut set 1, 1 dash, this current I1 is positive. Why? Because it is moving from left to right. Similarly, this current I2 is moving from right to left towards this line. So it is taken as negative minus I2. And I3 again it is moving from left to right towards this line, this imaginary line. So it is positive plus I3. And I4 is moving from right to left towards this line. So it is negative. So the KCL equation at 1, 1 dash is obtained as I1 minus I2 plus I3 minus I4 is equal to 0. Here it is to be noted that we can't take some part of the network for cutting. So here it is to be noted that 1, 1 dash is cutting the network into two parts. Here we can't take cutting line like this. Instead we need to take the cutting fully. So this is the basic idea of cut set matrix. Here we are using KCL not at nodes but at some lines, imaginary lines called cut set. Now let's consider graph of a given network, say this one. If we are drawing a line like above, say 1, 1 dash, this graph is divided into two. If branches 3, 5, 8 are removed due to line 1, 1 dash, the graph get divided into two parts. The graph become unconnected like this. Here we removed branches 3, 5 and 8 due to this imaginary line 1, 1 dash. So the graph become unconnected. It is to be noted that when we are connecting either 3 or 5 or 8 to this subgraph, the graph become connected graph. Now let's consider another graph. Here you can see there are two cut set 1 and cut set 2. Say this number is 2, 2 dash. Here line 1, 1 dash cuts the graph into two parts. So when we are considering cut set 1, this line 1, 1 dash cuts the graph into two parts. So the graph become unconnected. So this line 1, 1 dash is a cut set. The branch involved in this cut set 1 are 1, branch 2, branch 3 and branch 6. That is shown here. 1, 2, 3, 6 branches are involved in this cut set. Now just like earlier, when we are applying KCL at cut set 1, the equation become this branch current 1, that is I1 is moving from left to right towards this cut set 1. So it is positive, I1 is positive. Then branch 2 current, that is I2, which is moving from right to left towards this cut set 1. So it is minus I2. Similarly, I3, it is moving from left to right towards cut set 1. So it is positive plus I3. Then I6, it is moving from left to right towards this cut set. So it is plus I6. So the KCL at cut set 1 is obtained as I1 minus I2 plus I3 plus I6 is equal to 0. Similar way, when we are considering cut set 2, the branches involved in cut set 2 are branch 6, branch 4, branch 2 and branch 5. When we are applying KCL at cut set 2, this I6, what is the sign of I6? It is moving from left to right towards cut set 2. So it is positive. Plus I6 will come like this. Similar way, when we are considering fourth branch current I4, it is again moving from left to right towards cut set 2. So it is taken as positive. I4 is positive. Then what about I2? It is again moving from left to right towards this cut set 2. So it is plus I2. Similarly, when we are considering I5, it is moving from right to left towards this cut set 2. So it is minus I5. So applying KCL at cut set 2, we got the equation I2 plus I4 minus I5 plus I6 is equal to 0. So what is a cut set? A cut set is the minimal set of branches in a connected graph such that removal of these branches causes the graph cut into two parts. That is, the graph becomes subgraphs, two subgraphs, which are unconnected. Graph becomes unconnected. Basically, cut set may be of normal cut set or fundamental cut set. Normal cut set we already seen. So the graph is get divided into two subgraphs which are unconnected. So that line which divides the graph into two parts is known as cut set. So a cut set in which it contains only one twig is called a fundamental cut set or F cut set. What is twig? Twig is the branches of tree. So in order to build F cut set, fundamental cut set of a given graph, we need to draw any tree of the graph. So this is the complete graph. From this graph, we are drawing a tree such that it should interconnect all the nodes without any closed path. So we took this tree. The branches of this tree is 1, 2 and 3. The branches of tree is known as twig. That is, twigs are 1, 2 and 3. The complement of tree is known as co-tree. Its branches are usually termed as links. So the branches of co-trees are 4, 5 and 6. So in order to build F cut set, first of all we need to draw the tree of the graph. We took this tree and we draw co-tree by means of dotted line like this. So step number 1 is draw one tree of the given network or graph and mark the quadtree using dotted lines. So we selected this tree and quadtree is marked by means of dotted line. What is next step? Step 2 is identify fundamental cut set. Fundamental cut sets are those lines which will divide the network into two parts where there will only one tweak is present. So when we are considering this cut set 1, this green line, so here we can see that only one blue line is available. That is, one blue line means only one twig is available. So if in a cut set line, if there is only one twig and remaining branches are links, then that is fundamental cut set. So fundamental cut sets are defined for a tree. It is formed by one twig and a set of links. Number of F cut set is equal to number of twigs. So for each twig, there will be one fundamental cut set. So what is the relationship between number of nodes n and fundamental cut set? There is a relation. So we know number of twigs is always n minus 1, where n is number of nodes. So for this graph, number of available twigs are 4 minus 1, that is 3. So number of twigs of a graph is always n minus 1. For this case, it is 3. It is obtained as 3. Then direction of fundamental cut set is the direction of twig. So here I marked a green lines arrow like this. So its arrow is decided by the direction of twig 1. Similarly, for cut set 2, the twig presented is 2. So the cut set direction is decided based on the direction of twig 2. So it is marked like this. Similarly, for cut set 3, the direction of cut set, this direction is decided by the branches, that is twig involved in that cut set. In cut set 3, the twig direction is this one, therefore this direction is obtained. So that is mean by this point. Direction of F cut set is the direction of twig. So in fundamental cut set, it is to be noted that only one twig is available. Remaining elements, remaining branches are links of the graph. So step 1 is draw any tree and mark quadtree by means of dotted line. Then second step is identify fundamental cut set. So here 3 cut sets are available. Cut set 1. So the branches involved in cut set 1 are branch 1, branch 4 and branch 6. In cut set 2, the branches involved are branch 6, branch 4, branch 2 and branch 5. It is mentioned here. And cut set 3, the branches involved are branch 3, branch 5 and branch 6 as mentioned here. So what is the next step? Step 3. Here in each cut set, we need to apply KCL. So step 3 is apply KCL at each cut set. Here, as mentioned here, the direction of F cut set is the direction of tick. So here direction of tick current is taken as positive. Let I1, I2, I3 etc. up to I6 be branch current corresponding to branch 1, branch 2, branch 3 up to branch 6. Then in order to apply KCL at each cut set, we need to use this rule. Qij is equal to 1 if branch J has same orientation as that of cut set I. It is equal to minus 1 if branch J has opposite direction to that of cut set I. And it is equal to 0 when branch J is not in cut set I. Let's consider cut set 1. In cut set 1, what are the branches involved? Branch 1, branch 4 and branch 6. What is the direction of branch current and this cut set direction? They are same. So their sign is positive, I1. Then branch 4 direction and cut set direction is orientation is same. So their sign is positive, I4 is positive. Then I6, what is the direction of I6 and cut set direction? Same direction. So that is positive. So the KCL at cut set 1 is obtained as I1 plus I4 plus I6 is equal to 0. Similarly, when we are applying KCL at cut set 2, the branches involved are 2, 4, 5 and 6. What about the direction of branch current 2 and cut set direction? Same, positive. I2 is positive. I4, the orientation is similar to or same as that of cut set 2. Their sign is positive plus I4. Then I5, what about I5? So from this graph, it is very clear that the orientation of cut set and branch current I5 is opposite. So its direction is, its sign is minus I5. And I6 direction is same as that of cut set 2, so it is positive. So the KCL at cut set 2 is obtained as I2 plus I4 minus I5 plus I6 is equal to 0. Similarly, when we are applying KCL at cut set 3, this sixth branch current, third branch current direction is coincide with the orientation of cut set 3. So I6 and I3 is positive like this, I3 plus I6. But I5 is opposite to the orientation of cut set 3, so it is minus. So the KCL at cut set 3 is obtained as I3 minus I5 plus I6 is equal to 0. Let this be equation number 1. Now we can represent this equation number 1 in matrix form. Here in matrix form, the column is branches, number of branches 1, 2, 3, 4, 5 and 6. And row entry is corresponding to number of cut sets. So row entry is cut sets 1, cut set 2 and cut set 3. So when we are considering cut set 1, I1 quotient is positive plus 1, I4 quotient is there, that is plus 1, I6 quotient is plus 1 and remaining entries are zeros. Similarly for cut set 2, I2 quotient, I4 quotient and I6 quotients are positive plus 1. And I5 quotient is minus 1 like this. Similarly for cut set 3, quotient of I3 and I6 are plus 1 and quotient of I5 is minus 1. So this is the matrix representation of this equation number 1. So this matrix representation we can represent in compact form like this. So this matrix is nothing but our required matrix, that is Q matrix, that is cut set matrix. So this matrix is cut set matrix and this matrix is branch current matrix and this is null matrix. So in compact form, this can be written as Q into IB is equal to 0. So this equation we got by applying KCL equation at each cut set. How many cut sets are there? 3 cut sets are there. That is n minus 1 cut sets will be available, fundamental cut set will be available. That cut set by the column branches, number of branches, that is the size of this cut set matrix, fundamental cut set matrix. So there is a simple way in order to find out the Q matrix, that is cut set matrix. The size of Q matrix or cut set matrix is number of cut set, fundamental cut set into branches. How many fundamental cut sets are available? N minus 1 fundamental cut set will be available, where n is number of nodes. Here 4 nodes are available, so 4 minus 1, 3 fundamental cut sets are available in this example. And how many branches are there? 6 branches are there. So the size of Q matrix, fundamental cut set matrix in this example is 3 by 6. Let's see the simple method in order to find out Q matrix. So when we are considering cut set 1, so this is your cut set 1. Branches involved are 1, 4 and 6. So we can put 1 in these elements. Corresponding position we can put 1, 1, 1. So corresponding to first branch 1, corresponding to fourth branch 1, corresponding to sixth branch 1. Now we need to check the orientation of these branch currents. The orientation of I1, I4 and I6 are coincides with the orientation of cut set 1. Therefore, their sign is positive. There is no need of putting plus 1. It is defaultly known to us. The remaining entries are zeros. And when we are considering cut set 2 corresponding to 2 we can put 1, corresponding to 4 we can put 1, corresponding to 5 we can put 1, corresponding to 6th branch we can put 1. Now we need to check the orientation based on cut set 2. The orientation of I6, I4, I2 are same as that of the orientation of cut set 2. Therefore their sign is positive. but orientation of I5 is opposite to cut set orientation, so it is -1. Remaining entries are zeros. Similarly, for cut set 3, 3, 5, 6, 3, 5, 6, we can mark it as 1. Remaining entries we can mark it as zeros. What is the orientation? Corresponding to 3 and 6, it is positive. Corresponding to 5, it is negative. So this is the simple way in order to build Q matrix. Anyway, the relation is Q into IB is equal to null matrix. Q matrix into branch current matrix is null matrix. So that is the relation. If Q matrix alone you need to find, you need to use this one, this relation. Next, let's see the relationship between branch voltage and tick voltage. If you know the tick voltage, it is possible to find out all branch voltage. For that, let's see the relationship between branch voltage and tick voltage. We can represent tick voltage by Vt, and we can represent branch voltage by Vb, where B stands for 1, 2, 3, etc. up to 6 in this case. So let V1, V2, V3, etc. V6 be branch voltages, and Vt1, Vt2, Vt3 be peak voltages. This is the branch voltage direction. The polarity of branch voltage is marked based on this current. Peak voltages are represented across each peak as Vt1. This positive polarity is here. Lower potential is at here. Here this is the higher polarity, and this is the lower polarity corresponding to peak 2, and corresponding to peak 3, this is the potential Vt3 with this polarity. And branch voltage, all branch voltage potential we can mark like this. This is a +1, minus based on this current direction. Here +1, here -1 will come. So this is V6, and this is +1, this is -1 for V5, and so on. So what is V1? Branch voltage V1 is nothing but this tick voltage itself. Branch voltage V1 is nothing but this tick voltage itself. So V1 is equal to Vt1. Similarly, Vt2 is nothing but V2 itself. V2 is equal to Vt2. V3 is equal to Vt3. And what is V4? Actually, V4 is V12. The potential between node 1 and 2 is V4. In order to obtain that one, we need to move from node 2 and move in this direction, and we need to add all the voltage drops. So here the voltage drops are Vt2 plus Vt1. So V4 is obtained as Vt1 plus Vt2. So this is V5. In order to obtain V5, you need to move from point 4 and to point 3 in this direction. So here we can obtain V5 as this minus Vt2 minus Vt3. So V5 is minus Vt2 minus Vt3. Then what is V6? It is the potential across these 2 points 1 and 3. In order to obtain that one, you need to move from point 3 and move in this direction and add all voltage drops. So what are the voltages? Here plus Vt3 is there, here plus Vt2 is there, here plus Vt1 is there. So V6 is obtained as Vt1 plus Vt2 plus Vt3. Let all these relations be represented by equation A. Now equation A we can represent in matrix form like this. So here this is the branch voltage matrix, and this is peak voltage matrix. We have already got Q matrix like this. So this matrix is nothing but it is the transpose of this matrix, that is Q transpose. Now we got the relation as branch voltage matrix is Q transpose into peak voltage matrix. This is very important relation. So the two relation which we got from this discussion is, one is this one, that is a Q matrix, fundamental cut set matrix into branch current matrix, that gives null set matrix. This is a KCL equation at each cut set. This is the first equation which we got in this discussion. So the second relation is branch voltage can be related to tick voltage, which is in terms of Q matrix. Q transpose into peak voltage gives branch voltage. So these are the two relations which we got in this discussion. Now let's conclude the 6 relations which we got from different matrices of graph theory. First matrix was incidence matrix. From incidence matrix, development of incidence matrix, we got these two relations. This is the KCL at node A into IB is equal to 0. A matrix is incidence matrix, reduced incidence matrix, and IB is branch current matrix, and this is null matrix. And from there, we got the relationship between branch voltage and node voltage like this. A transpose into node voltage matrix gives branch voltage matrix. And this is used for nodal analysis. Next, we developed the tie-set matrix. In order to build tie-set matrix, we created or we generated fundamental loops. From that, we got the KVL equation as B into VB is equal to 0. That is, tie-set matrix into branch voltage matrix is a null matrix. And also, we derived the relationship between loop current and branch current like this. B transpose into loop current matrix gives branch current matrix, and these are used for mesh analysis. And finally, we developed cut-set matrix. The relation which we got is KCL equation at cut-set. KCL at cut-set is this one, Q into IB is 0. Q matrix into branch current matrix gives null set matrix. And finally, we derived the relationship between peak voltage and branch voltage like this. Q transpose into peak voltage matrix gives branch voltage matrix. It is also used for nodal analysis. Now I am giving one homework to you, just like earlier videos. So here graph of a network is directly given. You need to find out incidence matrix, tie-set matrix, and cut-set matrix, fundamental cut-set matrix for the graph given below.